I'm Daniel. My design project was on heat exchangers, and there's the picture that the book used, which a couple examples of like common heat exchangers are like an AC radiator in a car, and just take the AC takes the heat and takes the hot air from the room and then puts it into the working fluid, and then has work from the electricity, and it compresses the air. I'm sorry, I'm getting off track. But the radiator in a car cools down the antifreeze in the car and like keeps the engine cool. So that's a couple examples of heat exchangers. So the description was, what are the best materials for a conduction limited heat exchanger? And conduction limited means that both of the fluids in the heat exchanger are liquids. So if you have a gas and a fluid, or well, a gas is a fluid. If you have a gas and a liquid, then you have to consider the convection, because with liquids, you just have the convection is rapid, so it's just conduction from the material of the heat exchanger, and that's what this case focused on, was conduction limited. So the function heat exchanger, the constraints are the pressure difference between the two fluids, and it has to be able to withstand chlorine ions, because I think they're using it for water as one of the fluids. And the operating temperature is 150 degrees Celsius, and then cost has to be somewhat moderate. And the objective is to maximize heat flow per unit area and or per unit mass. And then the free variables are the wall thickness and the choice of material. So all that said, the equations that are being used are for the heat flow, which is area times the thermal conductivity of the material over the thickness, and then the temperature difference. And then you have the elastic limit, which is the difference in pressure and the radius of the tube, and then the thickness. And then so you have the heat flow and elastic limit, and the only variable left that you can like eliminate for to maximize the heat flow would be the thickness. So you solve for one of the equations for T and then plug into the other, and then you get the equation in the middle. And the for the material indices, you can kind of just ignore the area and the temperature difference and pressure difference, because that's all not material dependent. So you end up with thermal conductivity multiplied by the elastic limit, and that's for unit area. And then for unit mass, you have to square the elastic limit, because it depends on the wall thickness and density. But this case study just mostly focused on the heat flow per unit area. And with the heat transfer coefficients, since it's conduction limited, you can kind of ignore the heat transfer coefficients compared to the thermal conductivity. So the selection, you have the pressure difference considered, or those are all the limitations, the constraints on it. And one of the best materials to use would be copper alloys. So you have a bunch of different copper alloys, and you plot it for thermal conductivity and elastic limit. And one of the cheapest options would be brass, but it's cheap and it doesn't have much thermal conductivity, or it has a lot of thermal conductivity but not much corrosion resistance. Sorry, and it's cheap. It's like the most cheap option. And then the next would be phosphor bronze, which is around this area. And then you have the brass down here. It's not as conductive, but it's a little bit more resistant to corrosion, and the cost is just a tad bit more. But then like the most practical solution would be aluminum bronze, because the cost is kind of in the middle, and it's got decent conductivity and elastic limit, and aluminum's fairly light. That's a couple examples are in here. Then the most expensive example, which is the most corrosion resistant, would be like up in here, the nickel or nickel iron, aluminum bronzes. All just, you add more alloys into it, it makes it more resistant to corrosion. but the thermal conductivity does go down. So those are 4 of the main materials to choose from copper alloys. And so in summary, the objective was to maximize heat flow for a heat exchanger, or to choose the best material to maximize heat flow for a heat exchanger. And the materials selected, the most practical one would be aluminum bronzes, and then if you had more money to spend, you would choose nickel, iron, aluminum bronzes. They just have a lot less corrosion resistance, and the rationale was because copper has high thermal conductivity and corrosion resistance. And then concluding remarks would be, the case also mentioned that when you're using like water, or in this case the seawater, you have like organisms in there, and they kind of like to bond to the copper, which will increase thermal resistivity. So if you choose one with more corrosion resistance, those organisms don't really like those kind of alloys. So I think it might be better off just to go with the more expensive option. So.
Hi, I'm Luke Schrodinger, and my project was to determine what materials are good for radomes. Radomes are the large dome structures that protect like radars and sensors. They can be like on the front of planes, or you'll see them on the top of like news vans. Yeah, so they shield microwave antennas from the environment while they're trying to minimize their interference with the sensor's performance. Because incoming signals are usually weak, so even like small attenuation of the signal can decrease the sensitivity of the system. They also must be able to withstand structural loads, load from air pressure doses, and sometimes high temperatures, whether it's supersonic flight or anything that's going to and from space. 2 critical material properties for performance are the dielectric constant epsilon and the loss tangent tan delta. That first equation is the fraction power loss. That F is the frequency of the signal, A is amplitude, and that epsilon naught is the permittivity of a vacuum, so that's kind of a constant. And then for thin shells, that turns into that other power loss equation. And then the other important equation is for stress. That's the stress created by the pressure difference on the radome. And substitute for the thin thickness and get this equation, which we use to get the 2 material indexes. The first one's more for performance, to see what interferes the least with the signals coming in. And the second one is more for strength. And when you graph that, you get this, which is pretty messy. So if you simplify it into just polymers and ceramics, those are what can handle the required temperature of about 300 degrees Celsius. And there's kind of a trade-off. The materials, polymers, they have lower dielectric losses, but they can't withstand as high loads and temperature limits, while ceramics aren't as great with the losses, but they can carry higher loads and last better at high temperatures. So to conclude, if all you care about is the losses, if you don't really need to worry about like having a strong structure or high temperatures, PTFE, polyethylenes, those are the best. But if you need something a little more sturdy, like what you see on top of like newscast vans, those really large structures like you saw at the beginning, you might want like glass reinforced polyester or PTFE. But what they usually use if anything's going to and from space is silica and alumina, because those handle the greatest temperatures. So to conclude, PTFE and polycarbonates are usually the most common you see. That glass reinforced polyester if you need more rigidity, and ceramics are the best for really high temperatures.